Hello. Hello. Why is it chat? Hello. Hello. Who do we have? Okay. Hello, Lunar. Hello. All right. Excellent. Good morning, Nadine. Awesome. Why is the chat? I wanted the chat in the thing. Hold on a second. How do I do this again? Okay. Why is the chat not? Okay. Good morning, Luke. Sorry, the chat's doing something weird. Good morning, Lunar for the double. Good morning, Mohammed. And there's Josh. I want to start. Why is the chat? Okay. Um, I don't know why the chat. Okay. Good morning, Josh. All right. Well, we'll just start. I don't. Oh, and there's Mark. Okay. Um. Oh, maybe that's why. Okay. 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 Um. Okay. Let's get going. And I hear someone's voice. Okay, let's just get go. So good morning, good morning, good morning. I feel like that's every yes. Good morning, Mark. Excellent. Thank you. Awesome. Okay. I want to quickly, I always say that. I want to summarize and crystallize where we ended up at the end of Monday. Um, so Omega. Oh, and someone should be on mute, maybe. Okay. Um, Omega is the big issue here. In fact, I'll go back to that page in a second. Like the big takeaway from Monday is this. I know someone's there. I'll get them in 1 second. Okay, who's that one? Okay. The takeaway from Monday was that if I'm using Z now on purpose, like the whole class started with X, right? It started with a mass going back and forth along some X axis. And we were trying to predict, and X stood for position. So we were trying to predict what is the mass's position at some moment in time, right? And well, that's what we were ultimately trying to predict. First, we noticed all of these things about a mass going back and forth on a spring that obeys Hooke's law. We noticed all, like if it perfectly or if it ideally or very, very well behaves Hooke's law, we noticed all of these things, like it'll conserve energy. It'll flip back and forth between a lot of kinetic, very little potential to a lot of potential, very little kinetic, back and forth, back and forth. We noticed that its velocities will flip back, will continuously move back and forth, just like its positions, but also that its accelerations will do that, and its jerks and its whips and it's like all of its derivatives. Like we noticed all of these things about when something is subjected to Hooke's law, right? Um, and we ultimately stumbled on a differential equation that we needed to solve or get a solution to, and thereby predict what x for that mass would be at any given time t. What I'm saying is, reason we did all that work, the reason we spent 2 weeks looking at all the properties of a mass spring system and then spent 2 days or whatever looking at the mathematics underlying our ability to predict a value for X at any value of T, what I'm now backing up to say, or what we by the end of last Monday, we're backing up to say, you know what? All that math that we did regarding a mass on a spring, all that math would apply, does apply, would be useful to us for any system that can be described by that mathematical equation, any system at all that behaves like a mass on a spring. So, what we're saying now from here on in is if you have any variable z, like I'm intentionally switching to use z when I mean any kind of measurement that depends on time, right? So could be number of centimeters on an x-axis, or could be number of radians on a back and forth swinging pendulum, or could be the strength of an electric field, electrostatic field, which will come next, or could be a temperature in some cloud, homework 3. Any measurable quantity that depends on time, call it z from now on to mean general dependent variable. If z can be described, oh, I shouldn't even say if and only. Well, just if. If z can be described by that differential equation where the second time derivative of z is directly proportional to z itself, like that's what we're really saying, right? If more specifically, if the second time derivative is equal to -1 times some positive constant times z itself, then that means that z, whatever z is, will oscillate harmonically. The value of z will go up and down smoothly, going through an equilibrium value and back through an equilibrium value and through an equilibrium value and back through, from a maximum to a minimum, back and forth, back and forth. The value of z will oscillate harmonically in a manner that could be described by this cosine expression, where at any given moment in time, z is some initial or maximum value of z times the cosine of some constant called omega times t. Like, so we're saying, so this is like a general finding now for any dependent variable that could be described by that differential equation. And so two things about that. One, we're saying that so even if you don't know, like homework 3 that's coming up after homework 2, they talk about the temperature in some weather system. We don't know. We haven't learned about weather in this class. We don't study weather in this class. I don't know much about temperature. I forgot it all from chemistry, whatever. But it doesn't matter. The point of homework 3, for example, is if you know that temperature could be described by that differential equation, that specific one, where the second derivative with respect to time equals negative times some positive constant times the variable itself. If you have reason to know that, then you automatically know that the variable will oscillate harmonically according to the equation z equals z naught cosine omega t. What do I mean by harmonic? Like, so oscillation means is any kind of cyclical or periodic motion. Harmonic oscillation is a very specific type of oscillation. What does it mean? Right now, what harmonic means is behaving in every precise respect, every mathematical and physical respect, just like a mass on a spring. That's why we study it for so long. From here on in, any system that we call harmonic oscillation, and that includes atomic systems in P-Chem. As I said, it includes like electrostatic systems. It includes like all these things in nature and in the lab. If we say something oscillates harmonically, we mean it can be described and predicted by the exact same math and physical laws, principles as a mass on a spring. So the mass on the spring now becomes our model for all of these like other systems in the world. and they can all be, there's different ways to describe, so I'm so a solution that works to the differential equation that describes them is this cosine solution. I'm not saying it's the only one. I'm saying it's the one we're using right now. But the cosine solution has this constant term tucked into it. Oh, no problem. Got it. Direct chat person. Thank you. No problem. The cosine expression. So that cosine expression is a solution to the differential equation. Again, the differential equation is what nature and physical laws present to us. Like the differential equation is really just a mathematically generalized way of saying Hooke's law is applying here. But then we had to unpack the differential equation and get a solution to it in order to predict the motion of that oscillator. I'm not saying here that this is the only that this z equals z naught cosine omega t is the only solution, but I am saying it is a solution that works and that we're working with right now. What I want you to notice, again, I'm just quickly sort of reviewing what we said on Monday. What I want you to notice is that that solution has a term, a constant term right before the t, right? That we call omega from here on in. And we're going to and omega becomes like a constant identifying characteristic of the harmonic oscillator. Any one given oscillator can, like, in other words, with any one given oscillator, with any one given mass going back and forth on a spring, you can't characterize it by its where it is. It's in a different place every single moment. You can't categorize it by how fast it's going. It's going a different speed every single moment. You can't categorize it by how the rate at which it's accelerating. It's not like a 9.8 thing. It's accelerating at a different moment at a different rate every moment. The way to characterize or identify or distinguish a given harmonic oscillator is by the rate at which it cycles back and forth, its wiggling rate. That is what's captured by this constant term known as omega. Omega will be the square root of whatever the constant of proportionality is in the differential equation. Like that's the key, that's one key takeaway. Omega will be the square root of what, that's why we call the constant of proportionality omega squared. Like it's a benefit of hindsight. We could have called that constant anything. We could call it B, we could call it C. Would we specifically square it? We call it omega squared. Number one, to remind ourselves and convince ourselves at any moment that, so in other words, this is just some. Omega squared means some positive constant. By calling it squared, we're ensuring that it's positive. But also, we're calling it omega squared because what we're saying is now that we've done the chain rule twice to test our conjecture, to take derivatives of our conjecture, that constant term in there will be the square of whatever the coefficient is right before the t in the cosine expression. So what I'm really trying to say here, I'm going to turn the page back and start doing equations again in a second. And then we're going to get to the unthingy things. Wait. No problem. Got you. Direct chat person. Got you. Um, all right, I'm going to say this now. Okay. In fact. Okay, what I'm trying to say here, sort of quickly, I'm saying I want to make a distinction. I'm talking about double equal signs right now. I'm talking about double equal signs right now, not triple. I'm saying that omega, like omega is always going to be the square root of whatever that constant is in the differential equation. There always is that constant in the differential equation. That constant is that positive constant there is what tells us this is a simple harmonic oscillator. I'm going to say it again. It because there's many, this is our first differential equation that we've ever seen, but it's just a differential equation. A differential equation is any equation that expresses a derivative as a function of the dependent variable. So a differential equation could have any kind of form or format. Right? The one that we're looking at, the first one that nature presents to us, is where the second time derivative equals a -1 times a constant times the variable itself. So there is a constant there. The square, and there has to be the negative sign. I'm going to say there could be a constant without a negative sign. There could be a positive, there could be a differential equation that looks just like that without a negative sign. That is a differential equation. It might have solutions, but it's not a harmonic oscillator. The negative sign is what's telling us that Hooke's law is operating here, that the force is continually restoring the system to some kind of equilibrium. So whatever the positive constant is, the square root of it will always be omega. Now, double equal sign, that omega, like numerically, could turn out to be like for a mass on a spring, that constant there, right, was K over M. When we first when we first applied Newton's second law to Hooke's law, we ended up with this differential equation d2x dt squared equals negative K over mx. The constant was K over M. So omega was the square root of K over M. In the case of a pendulum, like from the lab, number 2, it turns out that omega is the square root of G over L. In the case of like a sound harmonic oscillator or something, it might be like temperature over pressure. I know you can't see on the board right now. I'm going to switch the view on the screen in a second. But what I'm trying to make clear right now is what omega actually equals will differ from system from the type of oscillator to another type of oscillator. It's not always K over M. There isn't always a K. There isn't always a spring with stiffness. Sometimes it's a pendulum that has gravity or something, or sometimes it's totally something else. But what the omega will always be determined by, it's always some kind of expression of constant material properties of the system ingredients. Something like factory installations, like in the case of a mass on a spring, how stiff the spring is and how heavy the mass is, they together determined omega. Where, right, not how you set up the mass, but just what ingredient, not how you set up the spring, but what type of ingredients you're using. Omega double equal sign will always be determined by what materials were being put together to create this harmonic oscillator. Okay, that's what omega will always be, double equal sign. But what does omega mean? What is it? That's what's here on the first page. So this is now triple equal sign, right? Like what omega means, in short, is wiggling rate, oscillation rate, cycling rate, the rapidity with which the thing goes back and forth and back and forth. Again, I'm saying, and I will move on. I always say that. I will move on soon. But I'm saying, don't, like, yes, sometimes omega equals square root of K over M. Sometimes omega equals square root of G over L, etc. But what does it mean? What is the omega? It's the one thing about a cycling system that, at least a harmonically cycling system, that we can say is constant. We can't say the position is constant. We can't say the speed is constant. We can't say the acceleration is constant. But the rate, but if the thing is cycling back and forth, then the rate at which it goes back and forth is constant and is captured mathematically by this thing called omega. Omega is the angular frequency. It's the number of radians completed by the system every second. Radians sounds like angle. And raises the question, why are there necessarily angles involved in what I'm talking about? I thought I was talking about just a mass going straight back and forth on a horizontal line. Where are there angles? What I was trying to say on Monday, that I'm just again quickly reviewing now, is what an angle really means. What an angle really is a dimensionless fraction of a circle. And what it means then to a physicist, an angle is a section of a cycle. The whole thing that's happening now, why cosines are going to come into our life and all that, is we are looking at phenomena that are intrinsically cyclical. So we're taking the math of circles and imposing the math of circles onto, which is already known and already worked out, and imposing it onto the physics of cycles. The advantage of a circle, what we know about a circle is no matter how big the circle is, the ratio of arc length to, well, the ratio of circumference to diameter is always a constant. That's what we know about circles. It doesn't matter how big your circle is, going all the way around it will always be 3 times the length, a little bit more than, pi times the length of going straight across it. So we use that fact to capture what angles are in a circle. Like, what does it mean? What does it mean for one angle to be bigger than another? It means to take up a bigger portion of a circle than another. Regardless of how big the circle is, an angle is a portion of the circle. A right angle always looks like a quarter of a circle, no matter how, or it always is a quarter of a circle, no matter how big your circle is. And how can you capture that quarter of a circle? You measure the length of the arc that takes you from one point on the circle to a quarter of way on the circle. And then you divide that arc length by the length of the circle's radius. So in other words, so that it doesn't matter how big the circle is. An angle is a pure dimensionless fraction of a circle captured by how far you go along the edge divided by how far out that edge is. The dividing part is just to normalize it so that 90 degrees looks like 90 degrees to me and to you, regardless of how big of a circle we're looking at. Hence, from here on in, what is a radian? A radian is that amount of a circle, 2 pi of which makes a full circle. I'm going to say that again. The conversion factor for all of this, the anchor for everything we're saying from now on, is that 2 pi radians makes a full cycle. One cycle is 2 pi radians. If you want to picture that in your mind or have more of an intuitive sense of it, remember that pi is intuitively basically around 3. I mean, I know it's a little bit more than 3, but if you're trying to picture this, picture pi as 3. So what does that mean? It means 2 pi radians makes a full cycle. Essentially, 6 radians is a cycle. So what is a radian? What is a radian? If you're trying to figure out what the heck is omega, oh, it's radians per second, but what the heck is a radian? A radian is a sixth of a cycle. Not perfectly, but approximately. It's like 6.2 of a cycle, 6.3. But what it is just a sixth of a cycle. So when we're measuring radians per second from now, and so jump all the way to the bottom of this board, if you're trying to figure out what we mean by omega, we're talking about the rate at which something cycles back and forth, except we're just measuring it in cycle sixths instead of in full cycles. So what omega is the number of cycles you do per second times 2 pi, right? Each cycle is 2 pi radians. So literally, I'm not saying, I'm going to move on, but just to summarize what we said yesterday, the top part of this board, I'm saying there's one quantity that could capture the constant identity of a harmonic oscillator. Something that is going back and forth in the manner of a mass on a spring, something that's going back and forth and obeying some kind of Hooke's law so that it conserves energy, so that it smoothly goes back and forth in the same way that its velocities smoothly go back and forth, in the same way that its accelerations smoothly go back and forth, et cetera, and has its positions and its velocities and accelerations all alternating signs, alternating direction, all those things. Anything that oscillates back and forth in the manner of a mass on a spring and can be described by the same math is called a harmonic oscillator. And from now on, for a harmonic oscillator, the one way to capture it and describe it, the one constant way to identify the harmonic oscillator would be the rate at which it completes cycles. What I'm trying to say right now, as definitively as I can, what I think I said at the end of Monday is there's three different, yeah, well, there's three expressions that you could use to capture cycling rate, but they're all equivalent. If you know one of them, you automatically do know the other two. If you can picture one of them, even one of them, you're good to go because all three of them are interlocked with each other. Literally, what if F stands for standard frequency, if F is the number of cycles performed every second, then the unit of measurement we use to capture that is 1 hertz. A hertz stands for a cycle per second. So if something is cycling, in fact, we're going to do, okay, we actually do have time. We're going to do this in the chat. I'm going to warn you right now. I'm going to ask a couple of quick exercises for you to answer it in the direct chat. I won't, I won't even and I'll wait till I get like 3 people answering. And it's not a race because it's in the direct chat. I'm going to just ask you a couple questions here. Well, in a moment, but I'm going to summarize and say, I'm saying if you know the number of cycles that something performs per second, then you automatically know the number of radians that it performs per second because you just multiply by 2 pi. There's 2 pi radians in every cycle. Or similarly, if you know the number of cycles that something does per second, if you know it's hertz, its standard frequency, then you automatically know its period because you just invert that. If it's doing 5 cycles per second, then it's taking 1/5 of a second to do a cycle. I'm going to quiz you on that in a second, vocally for fun, in the chat in a second. I'm going to give you a couple exercises, but the summary is this: if you know one, you automatically know the other two. Why do we have all three? Why do we have to bother with 3 different descriptions of the same idea? Because period, capital T, is the one that is the easiest to measure in the lab and picture in our heads for everyone. Everybody can picture and measure how much time it takes to complete a cycle. What everybody needs to use in the math, however, is radians per second. Angular frequency, if you find it a little bit abstract or a little bit new or a little bit hard, you're like everybody else. It is a little bit abstract and a little bit new and a little bit hard at first. But omega is what is the math relies on because we're using the math of that we already know about circles to describe and predict the physics of cycles. So omega is what is direct to the math. Radians per second is what is direct to the math. Instead of cycles, thinking of cycle 6, thinking of portions of a circle because we already know trigonometry. So period is what you see in the lab. Omega is what you work with in the math. And F, standard frequency, is like the bridge between the two. It's kind of like the translator between the two. So we're going to do this quickly in chat just to make sure we're on the same page. So all of this is to say, omega means this. What omega means for any oscillator is the rate at which it cycles back and forth. That's the triple equal sign. What determines omega is the physical parameters of the system. So omega triple equal sign, 2 pi over t. Triple equal. But what it might double equal sign, square root of k over m. Please try to keep those straight in your brain. The definition of omega is not square root of k over m. That's what it would determine it for a mass on a spring. What it means is how quickly the spring is oscillating back and forth. Okay, so bottom line, yes, what we're saying ultimately here is the heavier that you put a piece of object on a spring and the lighter that you put an object on a spring and the stiffer the spring, the more rapidly it will go back and forth and back and forth. That's what we're ultimately saying here. Square root of k over m is the determining factors, and 2 pi over t is the actual definition, the rate that is identified by omega. So very quickly, just to make sure we're all together, because I'm talking so much, please answer in the direct chat. Let's say something, some oscillator has an omega of 6 pi radians per second. If a system, a mass on a spring, is oscillating at a rate of 6 pi radians per second, then then in hertz, what is its standard frequency? In other words, how many cycles is it completing per second? If it's completing 6 pi radians per second, if its omega is 6 pi radians per second, then what is its standard frequency in hertz? I'm asking, and I'm asking for answers in the direct chat. I just got a direct chat. Awesome. I just got 2 direct chats, which totally showed that they were listening to the question. I'm even going to say, since it's direct, both people in the direct chat are correct. So that's awesome. And you should definitely submit for points. But it doesn't give it, you all, the rest of you, I'm going to wait for at least one more. I just got one more, and it's also correct. That is awesome. And you can still, oh, great. I just got one more. Also the correct number. Slight disagreement on the units, but right. But yes, good. So I got 4 people in the chat, 5 people. Close. All right. Now, okay, close. Oh, wait. And you're in the public chat too. Okay. So you can definitely submit to both portals now. So and I'm glad, thank you for the guts and everything. Let me say to everybody 3, yes, the number 3 is what's happening here. I say 6 pi radians per second, and there's 2 pi radians. There's 2 pi radians in every cycle. So therefore, what did I just say? There's 2. I mean, yeah. Now you got it. Good. Right. There's 2 pi radians in every cycle. So if I say that the thing has an omega of, I'm going to write this example down so you can see it. Hold on a second. Hold on. I'm just going to write it down so we have it in our notes. When I say SHO, I mean simple harmonic oscillator. So if some simple harmonic oscillator, let me also switch. Sorry. Right. Okay. If some simple harmonic oscillator has an omega of 6 pi radians per second, then yes, every cycle is 2 pi radians. So the standard frequency would be right now. I did that in a kind of a funny way, but like I'm trying to divide. I'll do this more neatly. I'm dividing by 2 pi, i.e., I'm multiplying by 2 pi radians per. So I'm flipping the units. Right? There's 2 pi radians in every cycle. No, that's cool. No, that's fine. That's fine. Um, um, so if it's omega, and what I'm just trying to show everybody, I know this is like a simple example, or maybe a boring example, but it's like if something's going back and forth, I can say, oh, look at the angular frequency of that thing going back and forth and back and forth. It's 6 pi radians per second. And that sounds really abstract and obscure. Like, what? What do you mean radians per second? The thing is just going back and forth. And why is pi coming into it? Because all I'm really saying is if you divide my answer by my description by 2 pi radians that are in every cycle, I'm just saying you would cancel out the radians and you'd cancel out the pi's, and you'd end up saying, oh, that thing is making 3 full cycles every second. That's all I'm saying. And similarly, and one cycle is called 1 hertz. Excuse me. 1 cycle per second is called a hertz. So if the angular frequency is 6 pi radians per second, then the standard frequency is 3 hertz. And then I can ask you all, and I'm going to ask you in the chat, if its standard frequency is 3 hertz, this thing going back and forth, then what is its period? How much time in the direct chat? How much time is it taking to do a cycle, a complete cycle? So I'm going to wait. I'm going to ask that again. I'm asking in the chat. Oh, good. Awesome. I just got one person in the chat and they is completely right. Um, any I'm going to wait for more. So I'm going to say yeah, I'll repeat the question. Awesome. If something has this standard frequency of 3 hertz, so it had an angular frequency of 6 pi radians per second. We decided that meant it has a standard frequency of 3 hertz. My question now is, what's its period? If it's doing 3 cycles per second, then how much time is it taking to do a cycle? Awesome. I just saw another thing in the chat from a different person. Awesome. Close. Wait. Awesome. I'm seeing a lot more answers. Some of the, one of them. I'm questioning. Good, very good. So I'm seeing a lot of great. Yes, yes, yes. And what are the units of this? Those of you just put in a number. You might want to add units to it. But all of you, like, submit for points for doing this. So I'm going to wait for one. Well, I'll say, okay, oh, great, great, great. Yes, 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 yes. So the answer to this is if if F is 3 hertz, then T equals 3 cycles per second. Reciprocated, like, well, that T by definition is the inverse of F. Literally, it's the multiplicative inverse. The reciprocal. In other words, just bottom line, 2 quick things. Well, 2 things. So I'm saying what I'm trying to illustrate here. Omega is what's going to be spat out by the math. So you want to get your mind around omega. Omega is always going to be in radians per second. But even if you're looking at a system that doesn't seem to have any angles in it at all, or what? No, you would be correct. I was just about to address that person who's asking about the units of seconds. I would great, and please submit that for points. Perfect question. I'm about to address that. So first, let me say, I'm drilling this down I'm trying to drill this with all of you because I think for most people, and certainly including me, Omega, Omega is like gonna be part of our life for so long now, really kind of for the rest of the course. So it's like really helpful and important to get your mind around Omega. And Omega comes up every single time you have any kind of harmonic oscillator or anything built from harmonic oscillators. Omega comes up, and Omega is always measured in radians per second. But often it's describing systems that are just going straight back and forth, back and forth. So it becomes very hard for people at first to like understand why radians or angles or anything are coming up. They're coming up because an angle is a portion of a cycle. Really. A radian is a sixth of a cycle. So at the end of the day, when we say, and I want to say therefore, then pi make like 2 pi radians is a full cycle. That doesn't mean that you always need. Oh, sorry. Oh, sorry. Hold on. I think you might want to wait. Okay. That doesn't mean that you always, we might need to do one more example in a second because the pi thing also confuses people. The pi thing is coming up because there's 2 pi radians per every cycle. But again, I want to emphasize pi is just a number. It's a little bit more than 3. And yes, the digits go on forever, so it's easier to just use this symbol called pi, but it's just a number. And it doesn't mean you don't have to have pi in your number of radians. There's a such thing as a radian. There's a such thing as 2 radians. Radians don't only come in groups of pi. You can have 1 radian, which would be about a sixth of a cycle. But I'm saying that Oh my God, losing myself again. I'm saying that whatever you hear, when you hear something as an angular frequency of X number of radians per second, just divide that number by 2 pi in your mind to be able to picture how many cycles per second it's doing, and then just flip that number to know how many seconds per cycle it's doing. Once you know omega, you automatically know standard frequency and period, and those are easier to picture. Period is the easiest to picture and the most direct to measure in the lab. That's why both your first two labs are all about period. That's the kind of measurement you can get in a lab. But the math that establishes it and predicts it and all that all focuses on omega. So you want to be able to translate, among all three of them. But then there's this question in the chat about units. Notice I'm saying all the units work out. All the units do work out if you're careful and you look at the units do work out. But at the end of the day, whenever I see something written in cycles or in radians, I'm using radians and cycles as placeholders when I'm looking at the units. For a while, when I'm doing my calculations, I'm using them and I'm canceling them out, when appropriate and stuff. But at the end of the day, in my final answer, like notice this. Well, at the end of the day, in my final answer, the word cycle and the word radian can often just be crossed out because at the end of the day, cycle is not actually a unit of MKS, and neither is radian. They're concepts, they're important concepts, but if you really think about it, MKS, like standard, international units of space and time. The thing about meters, kilograms, and seconds.
Thank you.
Oh, sorry, hold on. I think we want to mute Juan. I think you want to mute. I think I can do it. Hold on
Yeah,
one second. Oh, hold on. I'm gonna mute him. I'm just gonna. Where is he? Yeah, Juan, you kind of want to mute. Okay, okay, okay. Um, um, okay, there's a question in the chat about like, was it okay? Someone's asking, when they wrote period at the end, they just wrote seconds, not seconds per cycle. Absolutely correct. At the end of the day, period is measured in seconds. When I'm thinking about it or relating it to standard frequency or something, I'm thinking about it as seconds per given cycle. But absolutely, it's correct and good to cancel out the word cycles at the end because if you think about it, a meter is not just a concept, it's a specific size. The thing that makes meter a standard unit is that there is a standard sized meter. And same thing with kilogram and same thing with second. But the whole nature of cycles and radians, the reason we like the whole nature of a cycle is a cycle could be any size. We're saying that a mass goes back and forth at a certain rate of cycles per second. It doesn't matter what the size of the cycle is, we're saying. Similarly with circles, a radian is a certain fraction of a circle, but it doesn't matter how big the circle is. That's the universality and the importance of a radian, is that it doesn't care how big the circle is. So the size of a radian, this is again why angles are kind of confusing. When you say this angle is bigger than that angle, you're not talking about bigness in the standard set. Like this is not big in the standard sense of this takes up a certain amount of space. We're saying it takes up a certain fraction of a circle, no matter how much space that circle takes up, right? So radians and cycles are not actually standard units. They're placeholders. They're things we're keeping track of when we're doing our calculations. In fact, specifically, a radian is a meter of arc length divided by a meter of radius. So the meters cancel out, and a radian and a cycle have in common with each other the fact that they are dimensionless. They don't actually have a size. So the person who's asking me in the chat, like, is it okay that they just wrote period as just seconds? Very okay. Very correct. I'm just saying seconds per cycle so you can see cancellations as I go. All right, so good question. So hopefully, all right, so I think I'm going to move on. If there's, I'm looking at the chat. Okay, getting rid of that. Okay, so we've got 30 more minutes. I want to now totally shift gears and talk about the unthingy things for like 30 minutes. Um, Is there anything I'm forgetting? I'm just making sure. I think we're good. So raise your electronic hand if we're good for me to just move on completely now. Thank you. Thank you. Also, that's two people, three people. Okay. Four people. Okay. Awesome. Five. Great. Oh, six people. Okay. All right. So I'm shifting gears entirely now. Okay. Um, oh wait, and July, thank you. Is that you're raising your hand saying I can move on or you have a question?
Just saying you can move on.
Oh, okay, thank you so much. Awesome. And you just used your voice, so you should definitely submit for points for that. Awesome. Thank you. Okay. Ooh, wait, what just happened? Okay, okay, okay. Okay. Um, So I'm going to move to the unthingy things. Again, I can't remember if I said this to you guys or not. I want to talk about the substance of the sheet now, like the purpose of it, what sort of the right answers are, and what I was looking for. But again, I think I said this already Monday. If you didn't get all the points, you can still totally resubmit it to get all the points. And it's and some of yours were super thoughtful and super awesome. And I'm not taking off points because I disagree with your answers. I love some of your answers. They were really creative, thoughtful and really expressive. If you didn't get all the points, it might just be because I want more diagrams. It might be that simple that I want more diagrams or more deliberate explanation of like each task or more self-sufficient document. Like I need to be able to read this document even if I don't know what the original assignment is, stuff like that. And again, if it's still unclear, if you look at the rubric and it's still good, you can talk to me in person. But of course, you could still resubmit it to get all the points. What I'm now talking about is the actual substance of it. So, um, okay, so it's 10, 12. Um, so I'm just going to go through it here. Task one. So let's say, I don't know if you can see this. Yeah, say these are my two things, or like a cup and a pen, right? Task one, however you draw it or however you try to do it, task one was place 2 points of mass at, well, here, task one was 2 points of mass, 2 points of space, 1 point in time. Yes, I think that is possible. And I think something like this is exactly that. It's not meant to be a trick. I'm trying to set up a contrast. I'm trying to show that some of these are possible and some of them are not. I think this one is possible if you just do like something like this. So the center of the pen is over here, the center of the cup or the center of the coffee that's in the cup is over here. They're occupying two different points, like pixels of space at 1 point in time. I think it's possible. I think most of you said it's possible too. I mean, stop me if you didn't, or if you have any discussion on that, but I think that one was possible. Then we had 2 points of math, 2 points of time, 1 point space, right? Now that's a different question. It's a little bit awkward, in fact. Maybe you never, but it is a question. Um, and that one I also think is possible, but it looks different doing it, right? It is a different situation. It's something more like this, dun 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 dun, dun and then dun dun dun, dun, right? Like you put here, this thing is over here at 43 degrees latitude, 73 degrees longitude, whatever, in 5 feet altitude and it's 3 o'clock. And now this pen is at the exact same point in space, but at a different point in time. Different situation, but also possible, right? Stop me if you disagree, if you did anything different. So that is also possible, I think. Then we asked 2 points of mass, 1 point of space, 1 point of time, right? And this one, so this is task 3. This one's it's kind of interesting, a little bit interesting. To cut to the chase, I think if you're, and by the way, notice we're not trying to get all crazy like quantum mechanical chat GBT. Like we're just trying to be intuitive, like normal people with normal macroscopic objects in front of us, but sort of defined by their centers. Like what seems reasonable and what doesn't seem reasonable. And whatever we mean by reasonable, maybe I don't know exactly what I mean by reasonable, but whatever I mean by reasonable, I'm keeping the same idea in mind throughout all the tasks. So I think having 2 points of mass at the same point in space, at the same point in time, i.e., not just, well, it's funny that I'm using a cup as an example. I'm not just saying something like random like that, like something like sort of approximate like that. I'm saying like, can the center of one literally be in the same pixel of space at the same instant as the center bit of the other? And most people for this said impossible. And to cut to the chase, I agree. Although it's funny that I picked a cup as an example here. I sort of did that by accident. I think this one's impossible. But there were many of you that did something very smart and very clever that I'm totally is not the reason I'm taking off points. In fact, I was impressed when many of you, or some of you, did some clever thing like say, well, wait a minute. If one of these objects is a cup, let's say it's an empty cup with no coffee in it or something, it's an empty cup. Couldn't I put the center of the pen in the center of the cup at one time? Or like, couldn't I put a munchkin inside like the center hollowed out portion of a donut? And wouldn't that be their centers at the same place at the same time? That's interesting. If you did that, I am not criticizing you at all. I'm actually impressed. That's very thoughtful. But here's the thing that's interesting about that. If you try to do something like make one of your objects like a container, and you put the other object like inside the container. And by the way, something like this is going to come up a lot in electricity in like a month. So it's great that you're thinking that way. But the thing is, the fact that you would have to go to that level to come up with a way to answer this question possibly shows something about the question. Like if you go to that level and you make one of your objects a container or take advantage of the fact that one of your objects is a container, you're actually secretly now changing the rules in a way, right? Because you're saying now I could put the center of this object of the pen in the center of the other object as long as there is no mass at the center of the other object, which is very clever. But it shows, wait, you had to dig out the other object in order to do that. The only way you could get the center of one to be in the center of the other is if one of them didn't have any mass at its center. So you're not actually putting two center masses at the same place at the same time. You're doing a very clever workaround, which just shows how smart you are if you did that, but also shows really the nature of the question is that no, actually, we can't have two things. We can't have two bits of mass at the same place at the same time. The only way we could sort of seem like we did is if we restructure one of them so that it just happens not to be at its own center. Okay? So I'm saying the third one is impossible. If we're going to keep the same definitions of stuff as we were using for the first two, then the third one's impossible. You can totally stop me if you don't like that, if you have anything to say. I'm not trying to cut off. I just want to get to the end. But we have 20 minutes. So if you want to stop me, feel free. But are we good? Should I go? Electronic hands, should I go on? Or have I lost everybody? Have I bored everybody? Can I go on to the task 4? Thank you. Thank you, Lunar. Thank you, Jalila. Thank you, Mohammed. Okay. So task 4 and others. And Mark. Thank you. Awesome. Okay. So task 4. Oh, whoops. Task 4 is now 2 points. No, sorry. Is 1 point of mass at 2 points of time or in time and 1 point of space. Now, this one confused a lot of people also because this wording is very unusual. It's not meant to confuse you. Oh, that's a yes. Oh, thank you, Luke. Okay, thank you, Luke. This wording is unusual. You don't usually like talk about life this way, but it's totally legitimate. It's saying, can you have 1 point of mass at 1 point of space, but at two different points of time? Okay, well, I'm to cut the check. I say yes, it's possible. Now, a lot of you didn't say that because I think a lot of you were actually kind of leaping ahead in your mind without realizing that a lot of you are really interpreting this question to mean what task five actually says. Like, so you got to take the words carefully. It's saying, can it be at 2 points in time at 1 point in space, or put another the other way around? Can it be at 1 point in space, but at two different times? Well, that doesn't mean you have to go like this or something. That would be no. 1 point in space, two different points of time means can I take this object and have it here at 10:22 a.m., but could I also have it there, that very same there at 10:23 a.m.? That's what it's saying, right? Could it be at the same place at two different times? Could I be in our classroom on Monday, the 10th of February, and be in our classroom on Monday, the 17th of February? Yes, right? That's what it's saying. And so I think it is possible. The flip of the, and stop me, but a lot of people say it's impossible. I honestly think because they get legitimately confused by the words. I mean, that's fair. And I'm not, if that is not why you lost point, if you didn't get all the points, that's not the reason. I totally get it if you thought that this was impossible. But what I'd like to know is now, do you see why it actually is? Like, is there any question on it? Do you see that it actually is possible? Um, well, I'll move on. Or is that a? Oh, thank you, Josh. I love it. I love it. And you're getting points. All right, awesome. So now we move to the last one. 1 point of mass at 2 points in space at 1 point in time. Right? That's different. And this is task. Oh. Okay, this is task five. So I say this is the one that's impossible. You cannot have something over here and over here at the same time. I mean, it could stretch. You could have a pen that takes up many, many points. But if we're defining the pen as we have for the all five tasks, if we're identifying the pen as a pixel at its center, that pixel cannot be over here while it's over there. Now, what does all this, oh, we're good so far, right? We have 60 minutes. Now, what does all of this say? It says a lot about space and time. It says that they're similar. It says that they're different. Um, it says a lot about space and time. And if I have time by the end of today, I want to backtrack and say some observations about the nature of space and time that this indicates. But the real thing that this indicates to me, or for the purpose of this class, um, is it indicates something about the nature of things themselves, of particles. Um, And here's how it relates to this class, specifically Physics 204. Hold on. Okay, let me back up for a second and say, oh. Cool, cool, cool. I see that in the director. Very cool. Very cool. I'm gonna get to that in a sec. Okay, I see. That's nice. Direct chat person, and there's only one, so you know who you are at the moment. Let me back up and say what physics in general, whether it's physics 203 or physics 204, what physics is in general is stuff in space and time. That's it, right? It's kilograms in meters and seconds. That's what physics is. What we are doing is predicting where something will be when, always in physics. So, physics is the study of stuff that occupies space and time. More specifically, what makes it like a science and everything is anything that occupies space and time in a manner that is measurable, reproducible, and predictable. That's what is meant by physics, and it's part of physics. If it so, I mean, like love might exist, love might be real. I mean, it is. I hope justice might be real, injustice might be real. They might even be more important than anything we ever study in physics. But physics doesn't study just directly speaking. Physics does not study love or justice because love and justice, whatever they are, they're in the world, they're in reality, but they don't occupy space and time in a measurable, reproducible, predictable way. I can't say the justice cloud is moving from Bed-Stuy to Crown Heights at a rate of 30 miles per day. Like I mean, I could say it, but that doesn't mean anything, right? Like I can't put measurements to the occupation of space and time of justice. So physics is about whatever occupies space and time in a measurable, reproducible, predictable way. That's anything that does. Okay, so what's that got? However, some things, anything that occupies space and time in a measurable, reproducible, predictable way is studyable by physics. But we have to have two physics courses. Why? Like, why didn't we just cover everything in 203? Some things that are living in space and time seem more thingy than others. Some things seem more tangible or material or massive or particular than others. Those things that very loosely, informally seem to be tangible or concrete or massive or touchable or distinguishable or identifiable or countable, those are all informal words. The formal word for those kind of entities, the kinds that we studied in 203, planets, baseballs, cannonballs, those things are called particles. Oops, sorry. A particle doesn't have to be, I don't mean it in a fancy sense right now. A particle, which is what we studied in physics 203, were particles. They don't have to be tiny. We weren't studying electrons in physics 203. They could be as big as a particle could be as big as a planet. It could be a baseball. It could be a ball. It could be a cannonball, a ballistic. A particle can be very large, but what it means to be a particle is to be particular, to be distinguishable from other particles, to be specific, to be tangible, to be what specifically to be a particle. Now, here's what I'm looking for if in your homework. To be a particle is to be a thing that is so thingy that it follows the pattern that you just discovered in tasks 1 through 5. In other words, specifically, what, and you, again, you could have said different things and gotten full credit, but what I was looking for if you look at the rubric, in your final answer for what do you think a particle is, it doesn't matter what the web says. It doesn't matter what fancy exotic definitions of like photons and stuff are. I'm not saying they're wrong, but like it doesn't matter. Like it doesn't matter. I'm saying now that you just tried to do various things, various activities with a couple of thingy things, You discovered that you could do certain things and you couldn't do others. What I want for your answer to a particle is an answer that is based on what you just discovered in those five tasks. I want an answer that would differ if your results from those five tasks would differ. I'll tell you the answer right now. Again, you could have said other things. You could still say other things for full credit, but here's what I'm really, where I'm going with this is what I just realized in the task is what makes a particle, what it means to be thingy, what it means to be touchable or concrete or massive or whatever. What it means to be a particle is it's an entity that occupies one space at one time and cannot co-occupy that space with another particle at a given time. In other words, I'm saying what it means to be a particle, actually, what it means to be a concrete object, no matter how big you are, what it means to be a particle is to live in space and time, yes, but to live in space and time in a way that disallows, that prohibits task 3 and task 5. Literally, if you are a particle, task 3 and task 5 are impossible. Let me be very clear on this. We still have 7 minutes. I'm saying the fact that you couldn't put two things at the same place at the same time, and you couldn't put one thing at two places at the same time, that maybe tells us something about space and time, but what it really tells us is what we mean by a thing. A thing is something, really, a particle is something that cannot be in two places at once and cannot share a place at once with another such thing, with another particle. The reason I'm going to say this again and again, so I'm saying, what is a particle? A particle is something that cannot do task 3 or task 5. A particle is something that does live in space and time. Hence, we study it in physics. Whether it's a planet or a baseball or whatever, it lives in space and time in a measurable, reproducible, predictable way. So we study in physics. But a particle specifically is something that cannot do task 3 or task 5. A particle is something that specifically cannot be in two places at once and cannot share a place at once with another particle. Why I'm going to say this over and by the time I say that, if you're thinking at all like, oh, that's all you wanted? Like, oh, duh. I mean, of course, things can't share spaces with other things. And of course, things can't be in the two places at once. Like, I've always known that. Like, why are you wasting my time, Yaverbaum? I'm wasting your time because hopefully I'm not. I'm saying all this because what's actually fascinating to me, what is actually fascinating to me is what I want to make absolutely clear with 5 minutes left, and that is all we need, is this definition of a particle would not be interesting. It would not be worth a full day of discussion were it not for the fact that particles are not the only kinds of things in the world. There are unthingy things in the world, in the real world, in the world of science. Let me say this a different way. I'm saying in order to study something with physics, it's got to live in space and time. It's got to occupy space and time in a predictable, reproducible, measurable way. Particles live in space and time in a predictable way, but particles can't be in two places at once and can't share space at once with another particle. There's tons of entities in space and time that can be in two places at once and can share a space at once with another thing. There are tons of entities, and they are real physical entities studyable by physics. It is those entities, the unthingy things, that are the study of physics 204. Physics 204. So all of physics is about stuff in space and time. Physics 203 was about particles moving through space and time, not subatomic particles, just particles like planets or whatever, baseballs. Physics 204 studies ultimately, like right now we're looking at mass on the spring, because if you put a bunch of masses on a, if you put a bunch of oscillations together, what you get is a wave, such as a water wave or a sound wave. That's the first topic really that we really care about in physics 204. Physics 204 studies things like, sorry, water waves, sound waves, electrical currents, electrostatic fields, magnetic fields, and ultimately what is known as electromagnetic radiation, or in other words, light. This is what physics 204 is about. We've got 2 minutes. I'm saying if you look at every single one of those things that I just wrote down, and by the way, heat would be another example of an unthingy thing, but we don't really study in physics 204. But sound waves is a perfect example. Sound waves, like right now, we've got 2 more minutes. I'm going to ask you to unmute, and I want at least one of you to interrupt me while I'm talking. I want you to talk rudely while I'm talking right now. We've got 2 minutes. I mean, you could tell me to go if you want. Right on, and you'll get points. As I'm talking right now, there's a reason I want this. I want one of you to use your voice, at least one of you, while I'm talking right now. Talk over me, please.
Is
Like,
it good enough?
that was perfect, Mark. Thank
Thank
you. That was perfect. Okay, so now check it out. Check it. Yo, check it. First of all, he should get points for that. You will get points for that. Second of all, if you heard Mark talking while you heard me talking, think about it. That means two sounds were in the same place at the same time for you. Not by accident, not by an aberration, but very much because that's how sound works, right? If you've ever listened to music at all, if you've ever listened to somebody sing while they play the guitar, right? Or two notes on the piano known as a chord, it's absolutely fundamental to your experience that more than one sound is occupying one space at one time. And each one of those sounds is not just in one place, it's spread out, it's in perpetual motion, known as a wave, right? Like waves intrinsically are unthingy things. They are like ghosts. They can be together at the same place and interfere and add their amplitudes together, as you know from other classes. We still have 1 minute. Or if you've ever worked in a theater, you can shine a red spotlight on the actor, and then you could shine a yellow spotlight on the same place. And the yellow spotlight does not knock the red spotlight out of its place the way a baseball would knock out a basketball, right? That's not an accident. It's real and it's predictable and it's calculatable and all of that. But waves and sound and light and electricity and magnetism are unthingy things. They are freaking real, but they're abstract and less tangible specifically because they can be in two places at once and they can share a place. So there's tons of unthingy entities in the world that are totally the province of physics. They're still moving through space and time, so we still study in physics, but we need a second course for them. This course is for studying the abstract entities, all ultimately known not as particles, but known as information. We are here not to study the trajectory of particles ultimately, but we are here to study the flow of information. Same rules of physics, different types of things. Sorry, I can't. I know we're done. We are done. But so we're here. Physics 203 was about the trajectory of particles. Physics 204 is about the flow of information, like numbers, vectors, whatever these waves and fields and everything consists of. Um, and so the entities we're discussing are more abstract. That's why the math gets more abstract. But I think it's more exciting ultimately. But whether you like it or not, that's what Physics 204 is about. Unthingy things. It's about entities that live in space and time, but can share space and time and spread out in space and time. Ultimately, the flow of information is what we're studying here. So, okay, that's it. That's class. And actually, I have to run. I'm really sorry. So, if you have a question or anything, yes, have a great day. Have a great day. I have to run. So, if you have a question or anything, please email me or text me or whatever. And we'll figure it out. But yeah, I'm late for something. Okay, but thank you guys. Have a great. Oh, have a great break. Yes, happy holidays. Awesome.